Okay, let's go ahead and take a look at this problem. Now, there are many problems that are similar, so we need to make sure we're paying very close attention to the directions. Now notice this is saying that the function graphed above is f prime of x. So this is actually the derivative graph. And what they're asking us to find is the intervals of increase or decrease of the original function. So let's start off with increase. Okay. So we want the increase of f of x. So how would we go about finding where the original function is increasing if we only know information about its derivative? Well, so this is the fun part about this. This is putting calculus together. So if we know that the derivative represents the slope of the tangent line, because that's the definition, derivative is the slope of the tangent line, right? Then what we know is that the slope of the original graph, whether it's positive or negative, is represented by the derivative. So if I'm looking at the y values right here of the derivative, these are positive values. And in fact, if I look at anything in this area going from here to here, do you see we have all positive derivative values? And then down here, we have negative, and down here we have negative. And then going back this other way, we have positive. So what's going to be important to us is where is our derivative switching from positive to negative. So we're going to say this x value, we're going to approximate it, right? Well, let's say maybe it's negative 1.7 there. That number right there looks like 0, so we'll say that's at x equals 0. And then this value right here, maybe we'll call it x equals 2.5. So if I were to answer the question, where is my function original f of x? Where's the f of x increasing? Well, it would be increasing wherever the derivative is positive. So therefore, I'm looking at all these yellow areas because that means I have positive derivatives. So therefore, I am increasing from negative 1.7 to 0 and 2.5 to infinity. So similarly, where are we decreasing? Well, that would occur whenever I have a negative derivative, whenever I have a negative slope. So therefore, we're looking at all those negatives. So we're going to say we're going from negative infinity to negative 1.7, and then from 0 to 2.5. And you'll notice we're either increasing or decreasing, unless the graph were to the derivative graph were to just hang out and go right on 0 and just go horizontally. But otherwise, wherever one stops, the other one's going to pick up because we switched from positive slopes to negative slopes, which means if my original graph, and I can kind of imagine, if we're going to graph this, it means for all of our values up until negative 1.7, my original function was decreasing. And it doesn't have to actually go through 0, it's just decreasing. Then after the 1.7, we've switched to positive slopes, which means my graph was now increasing up until 0. Up until 0. Then at 0, our next boundary was at 2.5, where we switched to negatives, where we had negative slopes up until there. So it means we were decreasing. Maybe we went through x-axis, maybe not. I don't know. Doesn't matter. And then after 2.5, our graph had positive slopes, so we're increasing. So you can kind of match this up. You could see we were decreasing, right, up until the x values of negative 1.7. Then we were increasing from 1.7 to 0. Then we were decreasing once again from 0 to 2.5. And then we were increasing, graph was going up until infinity. So this would be some version of our f of x. There's infinitely many options. This is just one of them. And it matches the derivative behavior because negative slopes means my original function was decreasing. Positive slopes means my original function was increasing. All right, let me know if that helps.